Hi, and welcome to the Stat 512 final project for Group 20. In this project, we will be analyzing the impact of several different statistics about the COVID-19 pandemic, including measures that were taken by the government to prevent the spreading of this virus. So first, let's look at a bit of the background. As of March 6, 2022, there were a total of almost 81 million confirmed COVID cases. Obviously, on a day-to-day basis, this number can bounce around quite a bit and vary a lot. However, this fluctuation is partially due to government policies, including things like mask mandates, stay-at-home policies, vaccine promotion, and financial aid, among many other variables. One of the key discoveries that came along with this pandemic was the new vaccine to prevent harmful implications of contracting this virus. On December 14, 2020, mass vaccination began across the globe. In the US, we began to see several steps taken to ensure all could get vaccinated as soon as possible. On April 18, 2021, all US states allowed open vaccination for all residents aged 16 and older. Later that year, on July 4th, over 67% of the adult population in the US had received at least one dose of a vaccine. Vaccines were said to play a critical role in the battle against COVID, and they continue to become more readily available to all age groups every day. Another area where we saw tremendous government implications was in the financial aid given due to economic struggles. The government got involved and did its best to stimulate the economy in several different ways. The first of these was through stimulus checks that were given out. We also saw lots of small business loans and assistance given out, as well as debt relief and payroll benefits. There were significant strides in unemployment benefits as well to help aid those who were laid off or let go due to the pandemic. One other major way that the U.S. government got involved financially was through assisting with food, housing, and bills for those who could not afford them. Overall, the U.S. used over $1 trillion in programs and tax credits throughout this time of need. In the early phases of the pandemic, masks were noticed to be a highly effective way to stop the spread of the virus. However, many different locations had different policies, and this carried all the way down to the state level. For example, New Jersey was the first state to mandate mask wearing as early as April 10, 2020, whereas Utah took over 6 months longer and did not mandate it until November 9th. Ultimately, these policies were a bit controversial, and only 39 states ended up requiring mask wearing.
So the home isolation policy is different for different group of people. We primarily have three different groups of people. The first group includes people exposed to COVID-19 but not on COVID-19 vaccinations. They are at risk, and after exposure, they need to stay home and quarantine for at least 5 full days. They cannot travel and have to get tested after the quarantine period. They also have to take precautions until day 10, wear mask, and other restrictions apply. The second group of people are them who were exposed to COVID-19 and but have COVID-19 vaccinations. After exposure, they do not need to quarantine but they should get tested, and they need to take precautions until day 10 and wear a mask. For the third group of people, they're exposed to COVID-19, had confirmed COVID-19 within the past 90 days. So for them, no quarantine is required, and they also do not need to stay home unless they develop symptoms, and they also need to take precautions until day 10 and wear a mask, and other restrictions apply. So for the general research question, we have is, are there any explanatory variables relating to government policy and medical treatment that can explain the daily increase in confirmed cases in Tippecanoe County in Indiana? Under it, 3 detailed questions will be statistically analyzed based on the following variables and point estimates. For the dependent variable, we have continuous data, which is confirmed cases increase, and for the independent variables, four continuous variables will be considered, which are vaccine increase, stringency index, economic support index, facial coverings, and for the categorical independent variable, we will have stay home restrictions. So in this slide, I will briefly explain the variables we used for our research questions. Confirmed increase is a dependent variable which is representative of continuous data. This is the cumulative number of daily increase of confirmed cases. For the independent variables, we have vaccine increase, which is the cumulative number of people who received at least one vaccine dose. Stringency index is the index that records the strictness of lockdown-style policies that primarily restrict people's behavior. Economic support index is the index that records measures such as income support and debt relief. Facial coverings is the standardized strictness of mask mandate in public space, ranging from -4 to 4, from less strict to more strict. Now, stay home restrictions is defined as a categorical variable in our models. It has four levels, um, ranging from no measures up to requiring not leaving house with minimal exceptions.
Our first research question was whether or not the test of governmental policies have a significant linear impact on the confirmed case ratio. To do this, we used the stringency index, facial coverings, and stay-at-home restrictions from our dataset. Stay-at-home restrictions specifically was a categorical variable with three different levels, so we had to make three different dummy variables accordingly in order to test this. Our statistical hypotheses, the null was that beta 3, beta 4, beta 51, beta 52, and beta 53 were all equal to 0, and the beta 51, 52, and 53 were those three dummy variables for the stay-at-home restrictions. Our alternative hypothesis was just that H naught is not true, which this specifically means that at least one of those linear predictors actually has a significant linear impact on the confirmed case ratio. For the first part of the assumption check for the MLR model, I plotted the residual plots for all the different explanatory variables, and it was somewhat alarming because as the explanatory variables increased, there appeared to be non-constant variance, which violates one of the assumptions of the MLR model. Along with this, the normal probability plot also has an extremely high skew towards the upper end of the distribution, and the histogram also shows a right skew. This means that there's most likely non-constant variance and also non-normality amongst these residuals. We further tested this by doing the Brown-Forcey test, which gave us a significant test statistic indicating that the null hypothesis was not true. This null hypothesis not being true means that residuals do in fact have a non-constant variance. In order to test the normality, we did the Shapiro-Wilk test, and this also attained a significant result, indicating that the residuals do not follow a normal distribution either. Due to these two tests indicating this, we will have to do a transformation to try to fix these assumption violations, otherwise the MLR model might not be accurate. The final assumption to check is the multicollinearity problem. First, to test this, we made the correlation matrix between the explanatory variables, and none of those had a very high correlation. All of them were beneath 0.9, which means there's no problem on that end. And then we made the VIFs to further test this, and all of those were approximately 1. They're all less than 10, which is the cutoff, so there doesn't appear to be a significant multicollinearity problem amongst the data. In order to fix the non-constant variance and non-normality problems, we attempted to use a Box-Cox transformation. We attained a lambda value of 0.14 repeating for the maximum likelihood estimator for lambda, and then redid the assumption checks for all the different assumptions. We figured out due to the Brown-Forcey test and the Shapiro test that there was still non-constant variance and non-normal residuals. Therefore, it wasn't risk sacrificing the clarity of the model in order to do this transformation. To attempt to remedy the non-constant variance problem a little bit further, we did the weighted least squares regression, and both the outputs are shown from this. We had to do 2 iterations on this in order to make the predictor stabilize. Following this, we did an F-test to test our null hypothesis. We ended up getting that the F statistic was larger than the critical value, therefore we could reject the null hypothesis of the 5% significance level. This means that we have significant evidence to conclude that at least one of the explanatory variables tested does have a significant linear impact on the case ratio. Or in other words, based off the question we asked, governmental policies do in fact have a significant linear impact on the confirmed case ratio. We also showed what should be done to test this with a lack of fit test. RStudio wasn't cooperating with the large data set we had due to the computing power available to us, so we couldn't actually run the test, but we showed the code that could be used and how to analyze it. We showed it with the stringency index and the economic support index, but if you use all the explanatory variables, this same method could be done in order to test it. And in theory, we would attain an F statistic smaller than the critical value, such that we fail to reject the null hypothesis, which indicates that we should include all of the variables. We also did the bootstrapping method in order to test the parameters of the model, as can be seen by the histogram of the different parameters, the normal probability plot, as well as the confidence intervals for each. We did this because this will give us a more precise estimate, because the previous WLS model has very strongly non-normal errors, so the bootstrapping method can be a little bit more precise and help us further test. And since none of these confidence intervals contain 0, we do have significant evidence that they should all be included in the model, which further backs up the hypothesis test that we did before.
Next, we come to the research question 2, which is to test whether the interaction term of medical treatment and facial covering policy do exist. So we assume beta 1,4 equal to 0 or not 0. So first of all, we'd like to check some assumptions first. And before that, we can draw the added variables plot for the two variables in this model. And it's clear that for facial covering, we do have a relatively large slope given other variables. And so we can see it definitely contribute to the model, of course. But for the people vaccinated, this variable just gave us a horizontal line, but we will see later whether it have enough contribution. And if we look at the normal QQ plot and the histogram, we can basically see a normal distribution of the data points. However, and if we take a look at the Shapiro test, which just gave us a pretty small p-value, which means we should reject the null hypothesis. And of course, for the Barbaroni test, we can also see we should reject the constant variance. So, which is basically because there's lots of influential points in this model. If we look at the student-length residue and height matrix and the Cook's distance. So we concluded that we do not have such kind of assumption satisfaction, and so we need to transform variables. After we transformed variable with the power of lambda, which maximizes the log likelihood. However, it seems like the Shapiro test and BF test also failed. So we concluded that it's not worth to sacrifice the clarity of the model. If we ignore the violations of assumption and go directly to the GLT test for our research question, we can build the reduced model and the full model and find the F statistic is 0.7, which is pretty smaller than the critical value, so we do not reject the null hypothesis, which means the interaction term is equal to 0. So we can treat the interaction of facial covering policy and the impact of vaccination as 0.
So here
The third research questions: does confirmed case ratio with no measures differ from confirmed case ratio with requirement of not leaving house with minimal expectations? We compare the two levels, which we set mu1 to -2 level of stay-home restrictions and level 2 for the mu4. And here is our hypothesis. The new hypothesis is mu1 equal to mu4, and the alternative hypothesis is mu1 does not equal to mu4. This is a process of making assumptions, and in the process we use different ways. What we want to get is about the relationship between level 2 and level -2. We used one-way ANOVA for this model and calculate 95% confidence interval recorded in the slide. After compression, we got the conclusion. Since 0 is not contained by the confidence interval, we are 95% confident that the difference between a ratio of confirmed cases with no added measures versus the ratio with the stay-at-home intact is greater than 0. Essentially, this means that the stay-at-home was effective in preventing COVID. Overall, based on the 3 tests conducted, we can conclude the following. First, government policy did have a significant impact on reducing the number of COVID cases. Second, however, we cannot tell whether the number of vaccinated people impacts the amount of COVID cases based on mask wearing. The third conclusion is the stay-at-home orders play a significant role in reducing the number of COVID cases. After doing all works, we found that there's some limitation in our study, and we also have some future suggestions. So first, we can use a cleaner data set, which could help make analysis more accurate. The data we used was missing and or omitted, so by instead using a complete data set, we could be even more thorough. The data we got is mostly continuous, so we could eliminate the time series within data sets so that each observation is independent. Moreover, in the future study, we can explore more transformations of X variables and take into account of higher order of them so that assumption violation does not exist. And it would be interesting to look at the impact of government policies at various regions to see how politics play into COVID positivity rate. Another detailed thing is using higher computing power, such we could do the complete length of fit test for question 1. Last, there is our references page. Thank you for listening.